Okay, get this. What if I told you that you could measure a microscopic angle on a silicon chip just by looking at its color? It sounds wild, I know. But today we're diving into this really clever scientific paper that shows exactly how to do it, turning a simple digital photo into a seriously powerful measurement tool.
So that's really the big question here, isn't it? How on earth can a simple picture, a photograph of silicon, tell you about its precise microscopic shape? I mean, we're talking about the material at the very heart of all our computers. The answer, as you're about to see, is just so elegant. All right, so our story really starts with a colorful clue, one that was kind of hiding in plain sight the whole time. We're going to step into the world of materials science for a minute, where some researchers were dealing with a really tricky measurement problem. And the solution they found, well, it didn't come from some huge, complicated machine. It came from a simple, almost beautiful observation about silicon itself.
First things first, let's really get a handle on the challenge they were facing. What was the big problem?
So what the scientists needed to measure was something called the wedge angle. Okay, so imagine you take a slice of silicon that is impossibly thin, and then you punch a tiny hole in it. Well, that edge of the hole, it isn't a perfect 90-degree drop. It actually has a very slight slope. And the angle of that slope, that's the wedge angle. The thing is, we're talking about a feature that is so small. I mean, microscopically small. And your traditional measurement tools, they're often way too complex or too slow, or honestly just not accurate enough for this kind of job. It was a real headache for the people doing this research.
But then, the breakthrough. The key wasn't to, go out and build a better, fancier ruler. Nope. It was to decode a secret that silicon had been hiding all along. So here's the core idea, the big aha moment. You and I, we think of silicon as that gray, solid, opaque material, right? And it is, when it's thick. But if you slice it down to just a few microns, that's way thinner than a human hair. Something really amazing happens. It actually becomes transparent. And even cooler, the color of the light that passes through it starts to change depending on its exact thickness.
And check this out. It's not random. It's totally predictable. Just like the original paper says, the color shifts in a very specific order. It goes from red to yellow and then to white as the silicon gets thinner and thinner. And this predictable link between thickness and color, well, that's the key that unlocks this whole thing.
So, okay, how do you actually turn this neat color trick into a precise angle measurement? Well, it all comes down to a concept you probably remember from a middle school math class. They used the good old concept of rise over run. The scientists basically said, hey, let's treat that sloped edge like it's the long side, the hypotenuse of a tiny little right triangle. So if they could just figure out the rise, which is the change in thickness, and the run, the horizontal distance, they could calculate the angle. Easy. And the process itself is just brilliantly simple. You start with a basic digital microscope picture. From that photo, you can easily measure the run in pixels. That's the easy part. But the real genius, the really clever bit, is in step 3, calculating the rise by analyzing that color shift we were just talking about. Once you have those two numbers, the final angle is just a quick bit of trigonometry. Let's zero in on that rise calculation for a second, because this is really the heart of the whole innovation. What they figured out was that the ratio of green light to red light passing through the silicon was a super reliable way to measure its thickness. And you might be asking, why green and red? Well, it's because the intensity of those two colors changes in a very predictable way as that silicon gets thinner. And this right here, this is the magic translator. Now, don't worry, you don't have to memorize this formula. What's important is what it does. It takes that green to red color ratio from the photo, something a computer can measure in an instant, and it spits out a physical thickness. That's our rise. It's the bridge that connects the world of color to the world of geometry. Pretty cool, huh?
So a cool idea is one thing, right? But the real question is, does it actually work? Let's take a look at how this new technique stacked up against the older, more established ways of doing things. The results really do speak for themselves. I mean, look at this. When they tested it against the established, much more complicated methods, the new color technique held up incredibly well. For that first specimen, the results were almost identical. For the second one, they were absolutely within an acceptable margin of error. This proved the method wasn't just a neat party trick, it was valid. In fact, the average error across all of their tests was just 5.7%. Now, for a brand new technique that uses nothing more than a simple microscope and a digital camera, that level of accuracy is just fantastic. It proved the method wasn't just clever in theory, it was totally reliable in practice.
So, what's the big takeaway here? What does this all mean? Well, it means we now have a faster and, frankly, a much smarter way to solve what was a pretty difficult problem.
So, why should we care about this? Well, for one, it's a fast and reliable new tool that uses simple equipment that most labs already have lying around. But the bigger lesson here, I think, is about scientific creativity. It's just such a powerful reminder that sometimes the best solutions don't come from building a more complicated machine, but from just looking a little closer at the materials we use every single day. And that really just leaves us with one final thought to chew on. If silicon had this incredible, colorful secret hidden inside it all this time, what other simple, elegant solutions are just hiding out there in plain sight, just waiting for a curious mind to come along and take a closer look?